All right, well, welcome back. Hopefully you guys had a good day off on Monday. Um, we're going to go ahead then and kind of continue on in our discussion um, of where we are. Hopefully you guys saw your quizzes. I did get those recorded and grades in. Try to remember if there was anything big on that. Um, I do remember that the problem with the water coming into the house in terms of finding the velocity, that was all just because of the pipe shrinking down. You can use the continuity equation to get that, but then you use Bernoulli to figure out the pressure differential. Um, but I think in general, everything went okay otherwise. Um, so where we're heading, just so you know, we're moving to the next volume of the textbook. You may have noticed that on the syllabus, it said we were using volume 1 and volume 2. And if you kind of looked at the schedule, we started increasing our chapter numbers, and then all of a sudden we went back to chapter number 1. And that's because we're at that point now where we're going to switch into volume 2. So if you were at a semester school, this would have been about the break from first semester to second semester. For us, it happens in the middle of second quarter. So just be aware of that. We're now moving into volume 2. It doesn't really change much. You still find the text in the same place. It opens stacks, but we are going to be going into volume 2. So we're in the last chunk of this class. What we're going to talk about for the remaining couple of weeks is thermodynamics. And thermodynamics, if you break it down, dynamic means movement, and thermo is temperature, heat. So we're going to be looking at how heat transfers, what it means, what heat is, what temperature is, and those kind of effects. So we're going to start today by talking about just heat, what it is, and what it does. All right. And then as we progress, we'll start looking at, the different materials, what they do, like specifically different phases of matter, gases specifically. And we'll talk about the different laws of thermodynamics and just kind of ride that out. So that's where we're going to go. It's going to be very different feel, because up to this point, we've still been doing mechanics. We've been looking at how things behave more macroscopic, bigger. We're going to start talking a little bit more about microscopic. That's really what heat comes down to is, what's happening inside things at a very, very small level, and kind of go from there. All right, so that's where we're heading. So let's just start with temperature and heat, because they're very different things. And this is going to be a place where physics terms are substantially different than regular people out in the world terms. Now, you're used to that. Things like work, for example. Well, heat is a great example. When we talk about heat in physics, heat is energy. Heat is just another form of energy. It usually has to do with, like I was saying, the microscopic world, what's going on in a material microscopically. But heat is a measure of energy. Temperature is not heat. Okay, so when we talk about, like if someone says, oh man, it's really hot, right? Or the heat is killing me. They don't really mean heat. They mean temperature. And temperature is a measure of activity in molecules. So as temperature goes up, there's more activity in molecules. As temperature goes down, they become less active. They kind of lose their energy. So temperature, really think of it as a measure of, I'm going to say thermal activity, for lack of a better word. Now heat, when we talk about heat, this is transferring energy. It's taking energy. It's the energy that's in this object. So you can really think of heat or as temperature as sort of a measure of heat. Okay. So the first thing that I want to share with you is what we call the zeroth law of thermodynamics. And I know that sounds weird to say the zeroth because we usually start with first, right? The first law or the second law. Well, this one, it's called the zeroth law because it was actually decided to be a law after there had already been a first law, a second law, and so on. So they kind of backtracked and they thought that it was more fundamental. So that's why we call it the zeroth law. But this has everything to do with temperature. So I'm going to go to the whiteboard so I can write it up here for you. Okay, so the zeroth law of thermodynamics. Now, this one, let me write it up and then I'll kind of explain. It says that if A and B are in thermal equilibrium, and B and C are in thermal equilibrium, then A and C are in thermal equilibrium. Okay, so first of all, what does it mean for things to be in thermal equilibrium, right? I threw that word up here, or that phrase here, a couple of times. But thermal equilibrium, what this means is that there's no heat transfer between the objects. So we are assuming that they are close enough that there would be heat transfer, because like, think about this. If we're going to send energy from one object to another, like let's say I'm object A and I'm going to impart energy into something else. I have to be close enough to affect it, right? Like I could potentially transfer energy into this whiteboard because it's right here. I'm not, however, going to be able to transfer any thermal energy into your pencil, right? The pencil that you've got in your hand, I have no chance of doing that because of the distance that separates us. But that doesn't necessarily mean that your pencil and I are in thermal equilibrium. Okay, so when I talk about no heat transfer between objects, I mean close, right? Close to each other so that it could happen. All right, so thermal equilibrium just means there's not going to be a heat transfer between objects. Now, in terms of what this really means, this means that they're the same temperature. So that's how we use temperature. We use it to gauge thermal equilibrium. So if there are two objects that have the same temperature, then they are in thermal equilibrium. Okay, so basically what this is saying is we've got three objects. Okay, so here A, B, and C. So A and B are in thermal equilibrium. B and C are in thermal equilibrium. This is saying then that A and C are in thermal equilibrium. Now, I know that probably seems silly because you might go, well, yeah, that totally makes sense. But it wasn't entirely obvious when they first started talking about thermodynamics and how this all plays out. But they realized that temperature is a way to actually measure thermal equilibrium. Okay, so that's the whole point of temperature, is just to measure thermal activity. Okay, so while we're here, let's just talk real quick about some of the different temperature scales. So for those of you from well, all of us live in the US, and so we know that here in the US, we use Fahrenheit. Right? And so the Fahrenheit scale, this is the one that we use here. And Fahrenheit is kind of interesting because, of course, 32 degrees Fahrenheit, this is where ice freezes. And anybody know the temperature at which water boils in
212.
Fahrenheit?
212.
Yeah, it's 212. This is the most asinine temperature scale in the world. Well, okay, that maybe there are worse. I don't know. It's the worst one I know of. But it's all based on when ice freezes, or when water freezes, and when water boils. I do want to attach to this that it depends on the air pressure. This is at 1 atmosphere of air pressure. Water boils at a lighter or lower temperature if there's less pressure. We know this living where we live, like the fact that maybe you're going to bake a cake or something and it says high elevation directions, right? When we boil water, it's going to be at lower temperature because of the lower atmospheric pressure. You can actually get high enough, so this low enough pressure, that water will boil at basically room temperature. That's actually bad because that means like your blood would boil. So it turns out that as the pressure decreases, this boiling temperature decreases as well. But this is at 1 atmosphere pressure. Okay, so we use the Fahrenheit, and where exactly it comes from, I don't know. I know it named after, a lord, like Lord Fahrenheit, who probably came up with this scale. But we are not going to touch this. We're never going to use Fahrenheit. Okay. So then the more metric scale, of course, is Celsius. And Celsius, for those of you who grew up in other places, you may know this one pretty well. I have a pretty good handle on it because I grew up near Canada, and my favorite radio station was Canadian, and so they were always giving us weather reports in Celsius. So I have a pretty good handle on it. Plus, with science, we use it all the time. But this one makes a lot more sense because the water freezing, of course, is at 0 and boiling is at 100. And seeing metric is all about powers of 10 and everything. This makes great sense. Sure, we'll freeze water at 0, we'll boil it at 100, and then break it down from there. So there is another name for this. It's a little bit older. I don't know if any of you guys know of it as this. When I was younger, they would often call it the centigrade. So if you've ever heard that, it's the same as Celsius. If you've never heard it, don't worry about it. But if you ever come across it, it means the same thing. But it makes sense if you look at the word. So cent is 100, grade is divisions. So this is a temperature with 100 divisions, 100 degrees from boiling to freezing. All right, so since we're not going to be using Fahrenheit, we're only going to be using Celsius. Let me give you the conversion. I don't know if any of you guys know this one, but the Fahrenheit equivalent to Celsius, it's linear. It's 9/5 C plus 32. And obviously, if you want to go the other direction, you just have to obviously solve it for the other variable. But these are your conversions from Fahrenheit to Celsius. Oh, here we go. So Ralph just looked up Fahrenheit is from a physicist, Daniel Gabriel Fahrenheit. Cool. Thanks for that, Ralph. Okay, so these conversions, these are going to allow us to get only to Celsius, but at least now we've got a way. If you want a ballpark, and this is one that I learned as a kid, you want to go from Celsius to Fahrenheit. All you got to do is roughly double it. Notice 9/5 is almost 2. And then add 30. So if you have a Celsius number, you double it and add 30, it's going to be ballpark, especially for temperatures that we're used to, right? Like think about freezing, doubled. 0 times 2 is 0, plus 30 is 30. That's pretty close to 32. And in fact, that doubling and adding 30 works perfectly at 10 degrees C. If you take 10 degrees C, double it and add 30, you get 50, which is exactly the Fahrenheit conversion for that. So if you think about it, most of the temperatures that we experience are not far away from 50 degrees Fahrenheit or 10 degrees C. So that's why that little double and add 30 is a great little check. All right, well, anyway, so there's Fahrenheit and Celsius. But it turns out that there's a third one that we use, and this is actually the big one for science, and that's Kelvin. So I know some of you have taken chemistry, and you probably have seen Kelvin there. So has everyone at least heard of Kelvin?
Yes.
Yeah.
Yeah, maybe not know exactly what it means, but okay, so there's the Kelvin scale, and I know that this was named for a Lord Kelvin. But the Kelvin scale, the conversion between that and Celsius is really easy. Is that the Celsius is equal, well, let's go to Kelvin. Kelvin is equal to C plus 273. At least that's the whole number that it's closest to. It's actually a little bit more. It's like 273.15. So really, the only difference between Kelvin and Celsius is the shift of 273. So it's pretty easy, just either add or subtract 273. And when it comes to us doing things, we're not going to worry about the 0.15. We're just going to put 273 because it's rare that that extra 0.15 is going to matter. So imagine if we were using Kelvin in like weather forecasts, because let's think about today, right? I don't know how warm it is where you guys are, but it's like low 90s for us down here in the valley. So if we were to look at that, the 90s, that's roughly 30 degrees C, which means in Kelvin, we're over 300 Kelvin. So you could just imagine if they're like, oh, the high today is going to be 300. People would lose their shit. Yeah. But anyway, it is Kelvin. Now, the one thing to realize about Kelvin is that these are actually dimensionless, meaning we don't use anything on it other than Kelvin. It's not degrees Kelvin, it's just Kelvin. So, for example, 30 degrees C is equal to 303 K. So there is no degree symbol. We just write 303 Kelvin. All right. So where the hell did Kelvin come from? Right? Like we see where Celsius makes sense. I think Celsius makes a lot of sense. Fahrenheit, yeah, nah, it just seems random. And just so you know, Kelvin is not random. It could feel random to you, this whole, well, we add 273. But It actually comes from somewhere. And basically, this is how Kelvin scale was created. There's one important value in Kelvin, and that's 0. Okay, so K equals 0. This is called absolute 0. So again, that's a term you've probably heard, but K equals 0, that's absolute 0. All right, now, where this came from. Well, they were looking at, whoever they were, probably Kelvin and whoever other physicists were working with him, they were looking at pressures of gases at various temperatures. So let's say we had some sort of a gas, and we're gonna, on this graph, we're gonna graph pressure versus temperature. So we'll make the horizontal one temperature, we'll make the vertical one pressure. So, and let's say that this temperature is in Celsius. So at 0 degrees Celsius, we go out and we measure the pressure, and we get this much. The gas gets warmed up, we measure another pressure. We warm it up again, we get another pressure. We cool it down a little bit, get another pressure. But what they saw was that this was pretty linear, that as long as you keep your volume constant, that pressure and temperature, they form a linear relationship. If you look at the ideal gas law, good old PV equals nRT, you'll see that they have to be linear. Well, anyway, so they took this and they basically just projected it back, and they had this line. Okay, so then they took a different gas. And they said, okay, well, let's see what happens with this gas. And so they get a different pressure at 0 degrees C, and they get some more pressures at these other temperatures, and they draw that line. And then they do it with maybe a third one and so on. And what they found was that all of these pressure lines, if you kind of drew them all together, they all had the same x-intercept. Okay, so there's this one point where this temperature would lead all of them to have 0 pressure. Well, that, my friends, is 0 Kelvin. So that's where they actually started Kelvin, at this temperature, so negative 273 Celsius. And then they used the same scale, so it increases by 1 at the same rate as the Celsius increases by 1. And that's why it's purely off by 273. All right, so kind of interesting that all of this led to 0 Kelvin, or to the same spot. Before we step away from this, let's talk a little bit about what that means. So what would that mean, reaching 0 Kelvin, reaching absolute 0?
There's no kinetic energy at all.
Okay, so let's think about what pressure is, right? Pressure is force per area. So when we talk about the pressure in a gas, it's all the gas molecules pushing against the side. Okay, so why are they doing that? As Bradley said, it's kinetic energy, right? These particles are moving, they're slamming into the wall, and that's creating the pressure. So if we cool it down, and we see this pressure is dropping, 0 pressure would mean there's no force being exerted by these molecules against the side. Well, that would mean there's no kinetic energy. So at 0 Kelvin, we no longer have kinetic energy. And this is no longer kinetic energy in anything. So basically what's going to happen at 0 Kelvin is stuff's going to start falling apart. And as such, we see this 0 as a threshold. It's an unattainable thing. We can never quite get there, and we'll never get past it because it wouldn't make sense to have negative pressure, negative kinetic energy. And so you guys are probably familiar with like the speed of light as a maximum speed. Think of absolute 0 as a minimum temperature. And in fact, that's why it gets its name, because there is nothing lower than that. So it is absolutely the lowest. It's absolute 0. Anyway, even space, outer space, isn't 0 Kelvin. I want to say like the average temperature in space is like, there's a 4 in it. It's either 0.4 or 4 Kelvin. I mean, there is actual, even out in space, there is some temperature, but it's not absolute 0. And in the lab, I know that we've gotten to fractions of a Kelvin. When I say we, I mean humanity, right? Not me. I've never played in a lab where we've tried to cool anything because that has nothing to do with marine science. So, but I do know that experimentally temperatures have gotten very, very low to fractions of a Kelvin. So anyway, so there's the Kelvin scale, and we're going to use this primarily, especially when we get to talking about gases and what's going on there. We're going to use the Kelvin scale pretty much exclusively. So get familiar with it, which means for those of you who grew up in the States, get familiar with Celsius, because the sooner you're familiar with Celsius, the easier it'll be to go to Kelvin, saying it's just shifted by 273. All right, so there's Kelvin. All right, so when things are in thermal equilibrium, there is no transfer of energy due to heat. However, if things are not in thermal energy equilibrium, there will be energy that gets transferred from one to the next. And that is thermal energy. So it's just like any other form of energy, it is conserved. But thermal energy is reserved for energy that's transferred from one object to another by way of heat. Okay, so let's talk a little bit about how that can happen. The first thing I want to talk about is I want you to realize that this is a one-way transfer. Energy only goes from higher temperature objects to lower temperature objects. It is possible to go the other way, but it requires work. It's not something that will happen naturally. For example, think about like a refrigerator, right? We make refrigerators colder, so we remove thermal energy, right? That's how you want to think about when things get colder, you're removing thermal energy. When things get warmer, you're adding thermal energy. So something like a refrigerator is removing thermal energy from the inside, but it's not around anything that's colder. So it's not going to happen naturally, but we make it happen by, having electricity go through and run everything. Same thing with like an air conditioner. And you can also do the same thing. You can add heat to something that's already hot, right? But that again requires some sort of work. Okay, well, anyway, so heat transfer only goes one direction, from the temperature, or the higher temperature object to the lower temperature object. Okay, so when you talk about something feels cold, so you reach into the fridge and you grab your nice ice cold, high quality root beer. And you'll say, oh my gosh, this is super, super cold. What you're actually feeling is the heat leaving your hand. So energy is leaving your hand, going into that ice cold beverage because of the fact that it's lower temperature. So that beverage is warming up, and at the same time, your hand is cooling. Okay, because that energy is being removed. Now, in a world where your body temperature isn't going to change again, because like we regulate our temperature, right? We're warm-blooded. So even though I've got my hand on that ice cold frosty root beer, my hand will stay at a warmer temperature than it would reach equilibrium normally, because of the fact that my body continues to pump in heat, physically pump it in, right, from my blood. But if it was just two objects, like let's go with you're a dead body with your icy cold root beer in your hand, right? Then what's going to happen is both your body and the root beer will achieve equilibrium and be the same temperature. This is actually one of the ways that they use to figure out time of death. I don't know if any of you guys like to watch shows like CSI or Law and Order, those kind of things, those kind of like procedurals. But often they'll find, the dead body, and they'll ask the coroner, "Oh, when did they die?" And they'll talk about, all kinds of different things. But one of the things they'll use is temperature. They usually go to some internal organ, and they'll go, "Okay, well, according to the temperature of the liver or whatever, we know that this person's been dead for X amount of time." And they're basically using this idea of heat transfer. When you die, your body quits producing heat, just because just think about the machinery, the heat factory has shut down. So you quit producing your own heat. So all of the energy in your body is now free to go to the environment. And it will go to the environment because except for on a day when it's really, really, really hot outside, right? But your body temperature will lower to that of the environment. And so then they just can, they have someone who's already done the math looking at how heat transfers through a body, and they can figure that out. So this sort of thing has lots of uses, but just remember, it's one way. All right, it's from higher temperature to lower temperature. All right, so what are the different mechanisms? How can we actually transfer heat? Well, I'm going to go back to the whiteboard. And it turns out that there are 3 ways that heat gets transferred. So I put here 3 ways to transfer heat. Okay, so the first is conduction. So conduction, this is actual physical contact. So go back to that icy cold beverage. So I've got my icy cold beverage in my hand. There's actual physical contact, and so the energy is getting transferred from my hand into my icy cold beverage. Now, what's actually going on, if we look microscopically, is it's a transfer of kinetic energy. Think about something with lower temperature. It has particles that are slower, got less kinetic energy. Now, when I'm in contact here, think about the particles that are in my thumb. They're moving because they're much higher temperature. Well, they keep slamming into the ones that make up the glass. We've already seen through conservation of momentum that some of the momentum from my thumb particles are going to go and get transferred into momentum of the glass particles. And sometimes that ends up increasing the velocity of these, right? Usually. So on average, these particles in the glass are getting sped up, getting more kinetic energy, meaning having higher temperature. Meanwhile, the particles in my thumb are losing kinetic energy because they're giving some of it to the ones in here, which means my thumb is cooling down. So go grab your ice cold beverage, put it in your hand. You will feel that your hand is getting colder. It's losing thermal energy. And at the same time, your icy cold beverage is getting warmer. All right, so conduction is actual physical contact. All right, so if you got physical contact, that's conduction. But you don't have to have physical contact. It is possible to not be touching. So a second way that we can transfer heat is radiation.
Quick question for
Yeah,
you.
go ahead, Bradley.
This idea has always bothered me. So you know how you go into like creek by college and it's really cold,
Yep.
and then the lake is usually a little bit warmer
Okay.
because the river's, fresh runoff, snow melt, But is it the lake moving more? Does the lake have more kinetic energy than the water in this river? Because I would
Okay.
think because the river's flowing, it would be warmer, but that's never the case.
Okay. So when we talk about the heat is kinetic energy, it's kinetic energy of the molecules that make it up. So think about this pen. So this pen has a bunch of molecules in it. Right now, though, the pen itself has zero kinetic energy, right? As a whole thing, it has zero kinetic energy.
Yeah.
But the elements that make up this pen do have kinetic energy, right? If you were to look really, really close at one of the molecules that makes the red on my cap, it's going to have kinetic energy. So the difference is microscopic, really, really, small particles versus macroscopic, the bigger picture. And that's kind of the same thing with the river versus the lake. So we do think of the river as having more kinetic energy because we see that water flowing. There's speed to it, but that's the wrong way to think about temperature, because if I take this pen and I drop it, I didn't really change its temperature, especially since it was just really, really short term flying through the air. But the molecules inside all have the same kind of average kinetic energy. So we want to think microscopically when we talk about kinetic energy and temperature. Does that make sense?
Yes.
Okay.
Hypothetically, though, could you stir water well enough that the temperature increases? Like, if you had like a super fast machine that was capable of agitating water, like more than we could naturally, could it actually increase in temperature just through the stirring motion?
Absolutely. Yeah. And in fact, that will occur. But it's also partially due to friction.
Oh,
In
yeah.
fact, it's
That makes
more
sense.
due to friction, right? Like you take your hands and you rub them, you'll feel them warm up, right? And that is an increase in thermal energy due to friction. The friction is doing work. So it's taking away some of the macroscopic kinetic energy
And converting it into thermal.
and it's converting it into thermal energy. It's then transferring that to microscopic kinetic energy. So what you were talking about, if you were to spin, you're to mix, like if you were to mix water, you are going to increase its temperature.
Okay.
Absolutely. But the majority of that is due to friction. So, but some of it would actually be due to increasing the kinetic energy of the individual particle.
Okay. All right, cool.
All right, so what about radiation? Now, this is another place that everyday usage kind of pisses me off, actually. Um, Radiation in the real world, well, in the real world, out there, is a bad thing, right? People hear about radiation and they start thinking about, mutant zombies and, all that kind of stuff. But radiation itself is not bad. Like you're getting bombarded by radiation all the time, right? That's what the sun is doing. That's the reason you can see is because there's radiation. But radiation, what we're doing is we're sending energy by way of electromagnetic waves. Okay, so radiation, this is due to EM waves. So when I say electromagnetic light, you could just say light as an example of radiation. But radiation, it's just transfer heat by electromagnetic waves. So have you ever done this? Someone you know has gotten a really bad sunburn, and you go and you put your hand, you can even do this to yourself. You got like a really bad sunburn, and you put your hand close, but not touching it, but you feel the heat. You know what I'm talking about, right?
Yeah, I do.
Okay, so, and if you don't know about that, how about next time you're cooking something on the stove, right? You got your pot on the stove and put your hands close. Or you got fire in your fireplace, or you're out camping and you put your hands close to the fire and they warm up, right? You don't actually have to put your hands into the coals of the campfire. You just have to get them close. That's radiation. You're sending out electromagnetic waves. You'll learn a lot more about this in modern physics, the actual process of radiation. But you are getting heat without actual contact. So that's another big way that we transfer heat. You don't actually have to be touching. And this can happen over much greater distances. For example, I get warmed up. I have an increase in heat due to something radiating energy that's millions of miles away. And so do you, right? The sun. The sun warms us up. We are super far away, but it emits a lot of radiation. That radiation carries energy. That energy can be transferred as heat. Okay, so there's number 2. And then the third one is convection. And convection is another one that doesn't really need physical contact, but kind of does. All right, and what this is heat that gets transferred due to a moving medium. So let me give you some examples of that. I don't know if you can see, but I've got in my room right now my fan going because it's kind of crazy hot. Okay, so one of the reasons that fans work, there's a couple for cooling, but one of the reasons that fans work for cooling is convection. So what it's doing is it's actually moving the air. And so it's causing the air to move in different directions. And so it's taking places that have, say, higher temperature, so greater thermal energy, and it's actually moving it to other places that have lower thermal energy. and basically giving it to them. So in this case, the convection's happening because the air is physically moving. I have no idea exactly which way it's going, but let's say that the fan is up top here. So here's our fan going around in circles. And it's causing the air to actually circulate, and that's creating heat transfer. So this happens with air, it happens with water. Like this is one of the reasons why Seattle has a very temperate climate. Even crazier if you go north from Seattle, you go up to Alaska, places like Juneau and stuff like that, are actually considerably warmer than other places at that latitude because the ocean is bringing water, or sorry, obviously bringing water, bringing heat from other places and causes it to warm up locally. So a place like Juneau will get way more rain than snow, as opposed to somewhere, say, in the middle of Canada at the same latitude. Okay, so convection is the third way. If you've ever heard of a convection oven, it does exactly this. It's got a little blower in it that helps move the air. And so anyway, so these are the three ways you can actually transfer heat. You'll talk a lot more about radiation in fourth quarter. Convection, I think really the thing to realize about that is that it really depends, like temperature change, it's going to be dependent upon surface area. So a greater surface area will lead to greater heat exchange. This is also kind of prevalent in evaporation. Evaporation is a whole other story. I don't want to go there. But anyway, so I'm not going to really talk about that. But I do want to talk about conduction. Because conduction, since it does require physical contact, it's more mechanical anyway. And it's the primary method of heat transfer. Okay, so here's what's going on when we have conduction. So I'm going to label these things, my two objects, with their temperatures. This red one is going to have T sub H. So that's going to be hot or high temperature. And then this blue one is going to be T sub C. So that's cold temperature. All right, so there are two objects. Now, heat is going to flow from the hot to the cold. So it's going to go in this direction. Unless we put in some energy of some kind, but I don't want to look at that. Okay, now just so you know, some of the things that we use, some of the letters we use. So first of all, for heat, we use the letter Q for heat. Don't ask, I have no idea why. But Q is the amount of heat, so it's an energy. Now, heat transfer, so this is what we're going to actually kind of measure here. This is a dq dt. So we're looking at the change in the heat with respect to time. So how quickly is this happening? Okay, so how this plays out. Let's put something between these hot and cold to be our agent of transfer. So let's just put like a rod or something. So it doesn't have to be a rod. It could be a column of air. It could be, you know, a tube of water. It could be whatever, but we got something here. Okay, now, if you want to actually calculate the dq dt, First of all, we know that it's going to depend on the difference in the temperatures. It's proportional to the difference in the temperatures. If the two bodies, we call these reservoirs. Okay, so the word we use is there's a hot reservoir and a cold reservoir. But if those reservoirs are really close in temperature, then the heat is going to flow very slowly. And that should kind of make sense, right? Because remember that it's a measure of internal kinetic energy, molecular kinetic energy. And if the temperatures are really close, the kinetic energies are pretty similar. So these slower ones are not really that much slower. So they're not going to speed up as drastically as if it were a lower temperature. Okay, so it's proportional to the difference in those temperatures. It's also proportional to the area over which this is happening. And so if this is a little rod, think of A as the area of the end of it. So here's our rod, and A would be this circular area right there. Okay. So this should make sense as well. If what we've got connecting them has a really big area, then there's going to be more chance for energy to get imparted because there are more molecules that can get excited from more of the ones in here that then can transfer down. I mean, really think about what's happening here. If this is let's say this is just a rod of copper or something, the elements in the heat in the hot reservoir start bouncing into the elements here. They then bounce into the next, to the next, to the next, to the next, and just sort of this domino effect. And then eventually the ones down here start interacting with the ones in the cold reservoir and start raising its temperature. Okay, so the area makes sense, that the greater the area, cross-sectional area, the faster the heat transfer will happen. Similarly, it should make sense that it depends how far apart they are. We'll let L be this length, but this time it's going to be inversely proportional. If it's shorter, then the heat transfer is going to go faster. If it's longer, then it's going to slow down. It's going to take a longer amount of time. Okay, so there's that A. And then there's one other thing that's going to matter, and that is, what is this material? How well does it allow this energy to transfer? So we have to put one more thing in here. It's just another proportionality constant kind of thing. It's going to be a K. So we'll have K times A times TH minus TC. All right, so that K is what we call thermal conductivity. And it's a property of the object itself. So different materials will transfer that heat much better than others. In general, metals have high conductivity, but not all of them, right? Some of them are lower than others. It really kind of depends. So I've got a book here that's got a whole bunch of different numbers here for you. So let me tell you what some of them are. They've got really funky units. They're watt Kelvin per meter. Yeah, just smile and nod. They're watt per meter Kelvin. So for example, aluminum is 205, copper 385, but then steel 50.2, right? So it really kind of depends. They do kind of bounce around, but those are kind of the numbers that we're seeing. Now you go to other objects like wood. Wood is on the order of 0.1. Wood doesn't really transfer heat very well. Glass, also low, 0.8. Brick, 0.6. Fiberglass, 0.04. Right? So it really depends on the material, but different things have different thermal conductivity.
So
Now,
that,
I'm
oh,
sorry, go ahead.
I'm sorry, I always hate interrupting.
No, go for it.
That thermal conductivity with different elements, isn't
Yeah.
that associated with their valence shells?
It definitely is associated with their molecular structure. I don't know if it's specific to valence shells or not. Sean might know that better, but it definitely depends upon their molecular construction. That's all, and Bradley always interrupts. Those are always good questions.
Okay, thank you.
Okay, so depending upon this K, we label things in different ways. There are heat conductors. There are insulators. So we'll talk about some things are insulators and some things are conductors. And it really just depends upon their conductivity. Now, you notice that I put heat conductor because later, next quarter in E&M, they'll talk about electrical conductors and electrical insulators. And it's similar. It's just instead of looking at heat transfer, you're looking at charge transfer. But we've got conductors and we've got insulators. And again, conductors are going to be the things with high Ks, with high conductivity, and insulators are going to be those with low, right? So like as I was reading, I was telling you like those metals were ranging from like 50 to 300, right? And then some of the other things on there like glass and wood were on the order of 1 or even decimal. And you can see why we use those for insulators. Like when you build a house, we don't usually make the house so that it's metal because the metal will transfer the heat in and out really easily, which means it will be cold in the winter and hot in the summer. Now we might have some metal on it, like to help protect it from the rain and all that, but there will be other layers that are better for insulation. Think about windows. What make windows really good for like, energy saving windows?
Like solar panels?
No, not solar panels. I mean like the good windows that you get that help keep the heat from transferring, so help keep your house warmer in the winter and cooler in the summer.
They're clearer.
Okay, they're clear.
They're not tinted.
They actually, a lot of them are double paned, so there'll be glass and another pane of glass, and then inside is, well, best would be a vacuum, because imagine if there's a vacuum. If there's a vacuum, there's no mechanism for conduction. Remember, conduction, we have to have physical contact. And in a vacuum, there's nothing there. So the only way heat would transfer is by radiation, which is going to happen for sure. But if you go and you look at like energy saving windows, they're actually double paned, usually with a vacuum or even air on the inside. Because air, while not a vacuum, still has very low conductivity, right? Or you think about what's in your house. If you look at the walls, so you'll have the interior wall of your house, the exterior wall of your house, and usually there's something inside, right? There's some sort of an insulation that's made of fiberglass or foam or something like that. But those are all materials that are designed to have a very low conductivity, which doesn't allow the heat transfer. So if it's really hot outside, it takes a long time for that heat to make its way inside. If it's cold outside and you're inside, you're trying to keep it warm, it takes longer for that heat to go from the inside out, right? So there are actual real things that we concern ourselves with, and conductivity is one of the big ones. It comes down to what materials they use to make your pots and pans. Like, think about it. Pots and pans tend to be metal. They tend to be metallic because they heat up faster. They heat up more evenly, which allows you to cook a little bit better. But there are plenty of things that are made out of glass. Here's a fun one. I don't know if any of you guys have any like glass pots and pans, but there'll be glass on the sides, but the bottom will have something else. It'll look like black. You know, it's usually some sort of metallic element, and that's designed in such a way. We'll talk about this after we come back from break, so that you can actually touch the glass and not burn yourself, as opposed to if it was all metal, you could potentially burn your hand. Like, I don't know if anybody's ever cooked with like something like cast iron, like out camping or something. And if you have like a cast iron pan or a griddle or something in a stove or on a fire, and you reach and you grab that, and you will burn the shit out of your hand, just because of how well it conducts the heat. So anyway.
Is that principle with the glass windows the same reason why thermoses are vacuum insulated?
Absolutely. Yep. Really good thermoses also have vacuums on the inside, and so that helps eliminate the conduction heat loss. Totally. All right, let's take a quick break. I feel like I've been talking forever. So let's come back at like 4:20-ish. So I'm going to go ahead and hit pause. All right. So what are some of the things that happen with heat? Well, there are a lot of effects that can occur, but let's talk about a few of them. The first I want to talk about is linear expansion. As objects get more heat, as their temperature increases, they tend to lengthen. They get longer. This really is due to that increased molecular kinetic energy. Just imagine, you have all the bonds that are formed when we create a molecule. As these particles start moving more, they start wanting to get further and further apart, and so those bonds get stretched. And so we actually do see lengthening of objects when they get heated. This happens regularly. You can see, for example, a great example I've seen are pictures of railroad tracks that got heated up. If they didn't leave a little space between them, they ended up bowing so much that they bent, and now the railroad is ruined. Engineers know this, and so they design things now to allow for that expansion. Another great place you see it is in bridges. If you've ever gone across a long bridge, like you've ever gone down to, like, say, the Bay, and going to San Francisco, you go over, say, the Bay Bridge. When you go over a long bridge, you'll hear a like ka-thunk, 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 ka-thunk as you go across. And what you're doing is you're hitting these little ridges, these little open spaces that they've got in bridges. Now, they're usually not designed as just like one big strip, because that's kind of bad. But what they'll look like are like your fingers, and they'll kind of be intertwined like this, so that there's still space in between them, right? Like you can still see parts of my face through the interconnected fingers, but it allows for stretching and coming together and pulling apart. Okay, and so that's what that's what you're hearing as you're driving over. You're feeling your cars drive over those little spacers, but those are designed to allow for that increase in length. So let's look a little bit at how that occurs, like the math behind it, and then we'll talk a little bit about where it's used, because we actually use that as well as just account for it. Okay, so we'll come back to the board here, and let's talk thermal expansion. So we're going to have some object. Again, I'm just going to make it like a little rod. So let's say we've got a rod of metal. Maybe it's copper or steel or something. Don't really care. But it has a given length at some point in time. Now, if we increase the temperature, so we add thermal energy, we're going to see it extend. So it's going to get a little bit longer, and I'm going to call that delta L. So delta L is the increase in the length. Okay, so the question is, how much does it actually increase? Well, some things that we know about it. We start creating a formula here. This delta L, 1, it's going to depend on the change in temperature. So if we increase the temperature by 5 Kelvin versus 100 Kelvin, we should expect that the 100 Kelvin increase is going to create more of an increase in our length. And so in this, we're going to put a delta T. And it is proportional to it. If you look at experiments, and hopefully we can pull this experiment off in lab. I have a pretty decent setup for it. I just don't know how well it'll transfer to my house, but we'll see if we can do this because it is pretty cool to see the increase in length that happens from temperature change. Okay, so it is going to be proportional to the change in temperature. Now, it's also proportional to the initial length. And this one might feel a little bit weird that it depends on that, but here's how I want you to kind of reason it out. So think about just like a little thin little chunk of that rod. Thin chunk. Okay, so that little thin chunk is going to create a certain amount of change. Well, the next little thin chunk does the same thing, and the next little thin chunk does the same. And so all of those little pieces are going to add a little bit to our total change in length. And it's going to depend on how many of those little slices we have. So if you kind of reason it that way, it makes total sense that it should depend on the initial length. But then it also is going to depend on the material itself, right? Is it aluminum? Is it wood? Is it glass? And so we're going to put on here alpha. And alpha, grab another color here. Alpha is dependent upon the material, and we call that the coefficient of linear expansion. And that's going to be totally dependent upon the material itself. Again, in general, metals have a greater coefficient of linear expansion. All right, so this is what's going to happen linearly. But we could also have changes in volume. We can also have changes in area, because that's going to happen too. Like if we wanted to, let's say we had a sphere. If we had a sphere, so a ball of some sort of metal, and we heat it up, it's going to increase in volume. So we're going to see a bigger sphere, right, as we increase our volume. And so the question then is, how would we figure that one out? Well, you can kind of play the exact same process and go, okay, well, that change in V, that delta V, it's going to depend upon the change in temperature. It's going to depend on the initial volume. By that same kind of rationale, any one little volume chunk is going to extend by the same amount. But then we use a different letter here. We use beta. And what beta is the coefficient of volume expansion. Which again is going to depend on the material. But they're going to have different values. Your alpha and your beta are going to be different, even if it's the same material. So if we were to look at the coefficient of linear expansion for copper, it's going to be different than the coefficient for volume expansion for copper. However, it turns out that it's related. So check this out. We'll do a little calculus. So what we know about volume is that volume, like if we've got a cube, let's go to the cube. Volume here is equal to L cubed. So if I want to look at dV dt, then if I differentiate this, I'm going to get 3L squared times dL dt. And that's from chain rule, right? We throw that dL dt because of chain rule. All right. So notice we've got that 3L squared. All right, well, let's start putting in our different values for like our volume and our time or temperature and stuff like that. Like let's look at this delta V. So if we go to say a dV, that's going to equal to beta times V times that dt. So from the volume one, since I've got that one written here, we're going to see that dV dt is equal to beta times volume, which is beta times L cubed. If you go back to the other one, the linear expansion, we're going to see dL dt is going to equal alpha times L. So let's put those in here. So we get beta L cubed is equal to 3L squared times alpha L, which gives us that beta is actually 3 alpha. And so what we find is that this definitely holds experimentally. It's not perfect, okay? It's not exact, but it's awfully darn close that the volume expansion is actually 3 times the coefficient for linear expansion. You can do the same thing for area expansion. It's probably not going to surprise you that you get it as twice the linear, because that's what's going to happen when you differentiate, say, an L squared. Okay, so there's definitely going to be change in length due to temperature. So let me show you how this plays out. Let's actually do an example. the math of it's actually really easy. But so let's say that we've got we have a measuring tape. And let's say that that measuring tape is made of steel. And let's say that it's 50 meters long.
Hey, Bruce.
Yeah.
I'm sorry, I don't think I heard this, but what was T again?
T is your temperature.
Okay, that makes sense. That's pretty obvious.
Yeah, so it's the change in volume with the change in temperature.
Okay, cool. Thank you.
You're welcome. Okay, so we got a measuring tape. It's 50 meters long when it's 20 degrees. All right, so then we take it outside where the temperature is 35 degrees. So it's a hot day. So we go out there. So here's my question is how much longer is it? All right, so let's just see. So here's what we're looking for. We're looking for delta L. It's going to equal alpha times L times delta T. So in terms of the L and the delta T, we've got those pretty easily, right? The L was 50 meters. The delta T, we should really do this in Kelvin. Doesn't really matter Celsius or Kelvin because when we're looking at a change, it's the same, but let's just get in the habit of doing Kelvin. So it's going to be Kelvin. And then we need the coefficient of linear expansion for steel. So this is something that we would have to look up in a book or something. But it turns out that for steel, its alpha is 1.2 times 10 to the minus 5. And the units on this, by the way, are per kelvins. So Kelvin to the minus 1. You can see why that has to be in order for things to cancel out and be left with just line. So we'll go ahead and put that in here. So what we find is that the length of that measuring tape has increased by 9 times 10 to the minus 3. All right, so do you have an idea of how long that is? Might help if I wrote it as millimeters.
Oh, well.
Okay, so it's increased by just about a centimeter. So I don't know, what is that about? Like, well, that wide. Who knows how wide that looks like on your computer screen, but it's a centimeter. Now, is that significant?
No.
I mean, it depends how precise we want to be, right? Like
Yeah, that's
being
true.
off by a centimeter could be a problem. And it's not just if we measured the whole 50 meters. I mean, if we only use, say, 25 meters, so we're only reading it from 0 to 25 meters, then we wouldn't be off by 9 millimeters. We'd only be off by 4.5. But we're going to be off by that factor, right? In fact, the factor that we're off would be this. So we're measuring actual length of 50.009 compared to 50, this is the factor that we're off. It's pretty small, right? It really is. It's not that huge. However, if we needed to be precise, it could be enough that it'd be a problem. All right. Well, anyway, so this is one of the things that heat will do, is it will actually change your length. But because it changes the length, it also creates stress. You remember stress, right? Stress and strain, I hope, kind of,
Yeah.
right? So there is strain because we have a change in length. There is a deformation, which means there's a corresponding stress. So let's look at that real quick. So hopefully you remember with tensile or compressive, we used Young's modulus. And so we saw that, let me put here stress slash strain. That Young's modulus was the stress divided by the strain. So we're going to have stress over strain. Stress was a force per area. And then strain was a measure of the deformation, right? It was the change in the length divided by the original length. Well, this part, there's actually going to be a piece that's due to thermal stress or strain, I mean. So if we were to kind of break this down, the strain has two parts. There's the regular old tensile plus the thermal. So the tensile is going to be F divided by A times Y. That just comes from solving this for strain, right? It's stress over Y, which is F over A times Y. Now, if we look at the thermal, remember how the change in length, it was A times L times delta T, but we're going to divide by its initial length. So that L just goes away. And so the thermal stress is just alpha times delta T. Okay, so there's your thermal strain. It's alpha times delta T. But now here's what I want you to think about. Here's my rod. As the temperature increases, this wants to extend. But let's say we were fighting that. We're going to apply a force on the ends to keep it from getting bigger. So the question is, how big would that be? How much force would we have to apply to counteract that? Well, that would be where the strain ends up being 0, because we're going to kind of cancel it out. So if you were to set this equal to 0, and we're just going to solve for looking at the stress, the force per area, we get force per area is going to be negative alpha times delta T times Y. And so this is actually your thermal stress, right? So thermal strain was the alpha times delta T, but the thermal stress is alpha times delta T times Y. So it depends on the material a lot. It depends on the thermal conductivity, or sorry, the thermal linear expansion constant. It also depends on the Young's modulus, which was a measure of its ability to react to stress, and also the change in temperature. Its opposite sign, notice it is negative. So basically this is just saying we have to do the opposite. So if it heats up, we have to apply, its thermal stress is negative because we need to add force to push against it. Anyway, so fun little fact that when things heat up, they change their dimensions. Their volumes change, their linear dimensions change, and so. All right, so there's one of the effects that we need to take into account and pay attention to as stuff gets heated. All right, the next thing I want to look at is how changes in temperature can occur, like how much heat we need to change temperature. So when I put up here, heat required to change the temperature. Okay, so let's again just think about what should matter. So first, it should matter the change in temperature. If I want to change the temperature of an object 5 degrees C, it's going to require more heat than 1 degree C, less heat than 10 degrees C, and so on. But it's definitely going to depend on the delta T. So that should make total sense. Another thing that is going to depend on is the mass of our object. Because something that's more massive has more material, which is going to require us to increase or require more heat for the increase in temperature. And then we're going to allow for some proportionality constant, which is going to be dependent upon the material itself. Okay, so this is going to be their heat required to change the temperature of an object by delta T. So this guy C has a name, and it's called the specific heat. Oops, maybe I spelled it right. Specific. So I'm going to call it the specific heat constant. Another name that it goes by is the specific heat capacity. So you'll see both of those words. So just so you're aware. Sometimes it's just called specific heat, but this is our specific heat capacity. So it's a property of the material. This is another thing that you can look up in a textbook or online, and you'll find all kinds of different numbers for different materials. So different materials have different C's. All right, so this is how we're going to measure how much energy we need to change temperature. I think this is probably a good place to mention a couple other things because I keep forgetting, and I probably should, seeing most of the world doesn't use metric. So we use joules for energy, right? But there are some other measures for heat. Let me put here heat units. Of course, you know joules, right? So good old joules. Another one is calories. Now you've heard this, and I'm sure when you think calories, you think food, right? Because we talk about, oh, that cookie has 500 calories. Don't eat
It's
very many of those cookies.
kilocalories, isn't it?
Okay, so here's another thing that we have to be careful about is that calories in the science world are not the same as calories on a box of food. Okay, so calories, I'm going to put below science. Science calories are such that 1 calorie is equal to 4.186 joules. And I know that that probably feels like a really weird number, but it was found by looking at changes in temperature of water. So it was looking at increase in temperature of water, and this 4.186, that actually comes from the specific heat capacity of water. So anyway, it's a weird conversion, but just like so many of our things that we use that are non-metric, they come from random places. Although this one's less random than others. It's actually based on a physical property of water. So in that way, it's kind of like, I guess, a little bit like Celsius. Okay, but there are also calories, as we know, and food. So I'm going to put here calories, food, calories. And the way that this works is 1 calorie. Now I'm not going to write CAL. I'm actually going to write the whole thing, 1 calorie. It's actually equal to 1 kilocalorie. So when you read on a box and it says there are 50 calories in this serving, it's actually 50,000 actual calories. So of course this means it's actually 4,186 joules. What's kind of fun is if you go to other countries and you look at their nutritional facts, their boxes and stuff will actually say kilocalories. So instead of reading 125 calories, it'll say 125 kilocalories. So yet another place where the US just does stuff flat out wrong. I don't like to use judgment often when it comes to this. Well, okay. You guys know I'm very judgy when it comes to metric and also when it comes to radians. But in my life normally, I'm not very judgy. But we as a country do things so wrong here. It's not 190 calories. It's 190,000 calories. And maybe this is done so people don't freak out and go, oh my God, I'm eating 190,000 calories. But as we know, it's a scaling factor of 1,000, whatever. But hey, let's be accurate. Anyway, so there's another one. Your food calories are actually 1,000 real calories. And then the last one I want to show you, and this is definitely my least favorite, is what we call the British thermal unit. Also known as a BTU. So you have probably seen BTUs. Usually you see it when it comes from, or when they're talking about like a grill or a stove or something like that, and they'll talk about BTUs. So these are British thermal units. Okay, so British thermal units are also kind of like the calorie, based on looking at change in temperature of water, right? So like a calorie, that's the amount of heat that's required to raise the temperature of 1 gram of water 1 degree Celsius. And I think it's specifically like 14 to 15 or somewhere around there. Okay, so the British thermal unit is defined similarly. It's the amount of heat that's needed to change the temperature of 1 pound of water 1 degree Fahrenheit. Yeah, I think you guys can hear my mental groan right there. Okay, so it's a pound of water, 1 degree Fahrenheit. Okay, what kind of bullshit unit is that? Okay, well, anyway, the conversion is 1 BTU is 1,055 joules. So if you ever have these other funky units, that's their corresponding conversions. I will deal with joules and calories. And I mean calories, not kilocalories, calorie. But if you have something like, if you want to try to actually figure out how many joules of thermal energy do you get from a box of Cheerios, you're going to calculate these calories, multiply by 1,000, get your, whatever. But other than that, barring that kind of thing, I'm going to stick with joules and regular calories. Okay. Anyway, I digress, but we kind of needed to talk about that. So when we look at the heat required to change the temperature, it's very linear. It's very linear for the most part. There are some exceptions. But basically, it's this easy. Let's say we want to heat up silicon. Okay. So maybe we're making some sort of a electronic circuit. So we got some sort of element in there that's made out of silicon. All right. And I want to look at how much temperature is going to increase when we have this energy flowing through it. Okay, so let's say that we're putting energy in. So we're going to say energy enters a circuit or a silicon element, or object, let's call it object, at 7.4 times 10 to the minus 3 joules per second. So basically, I just gave you watts, right? Joules per second or watts. So this is 7.4 milliwatts. All right, I will tell you that C for silicon is 705 joules per kilogram. And I'll even tell you that the mass of this thing is equal to 23 times 10 to the minus 3, or 23 milligrams. So it's tiny. It's only 23 milligrams. It's a little tiny circuit element. So here's my question, is what is the temperature change? So how much are we going to increase the temperature of this? All right, well, let's just go up here and we're going to solve this for delta T. So delta T, it's going to equal Q over C times M. So Q, we're putting in 7.4 times 10 to the minus 3 joules. The C is 705 joules per kilogram. And the M, well, we need to change that. So it's 23 milligrams. That one, if we convert that, that's 23 times 10 to the minus 6 kilograms. I forgot to put a Kelvin in here on our C. It's joules per kilogram Kelvin. All right, so we run the numbers on that. And you get 0.46 Kelvin. So it's going to go up half a Kelvin, just under half a Kelvin, every second. So just by pumping current through, you are going to increase the temperature of that object. But this is something you also know well, right? So think about this. When you have your computer going, you hear the fan blowing all the time. Well, that's one of the ways it helps mitigate this temperature increase. My phone, I imagine yours does too, if I'm using it for something kind of big, like mapping programs or something like that, it'll get damn hot. And that's because it's a lot more energy is going through, a lot more electricity is going through and causes it to heat up, right? So this is why electronics get hot, is because they're using the power. That power is energy. That energy increases the temperature. And especially in electronics, it's all about resistors. Resistors always get hot, always. All right, so specific heat. This C, it's dependent on the material. Different materials have different Cs. Here's another good example. Let me switch cameras. I don't like leaning over. Let me go over here. Okay, so have you ever had this experience? So you order a pizza and it comes to you nice and hot. So maybe you're actually at, at the place and they bring it out. And so you go and you grab your pizza, grab it from the end, from the crust, no big deal. You go and you take a bite and it burns your mouth like crazy. Ever had that happen? Don't lie.
Yeah.
I know you've all had
A lot.
Happen. Yeah, right? Okay. Now, obviously, it all comes out at the same temperature, right? And if you think about it, like you burned your mouth. Well, let's just take our finger, so apples to apples. So you touch the crust, and then you touch the toppings, and the toppings are still going to be way hotter, right? So the question is, why? Well, let's just think about this from specific heat kind of idea. Now, they're both exposed to the same environmental temperature. It's not that there's a little pocket of really hot that's over the center of the pizza and really cold over the outside, right? So it's all about the same. So we can think of the whole energy transfer as the same. We're transferring energy out of both of those things at the same rate because of environment. Okay, now, so they both lose a certain amount of energy. Let's call that X. They lose X amount of energy. Now, the crust, though, this amount of energy causes a much greater change in temperature than over here. So if you look at that formula that we were just playing with that Q, right? The Q's are the same. Q's are same. And even if we sort of adjust it per mass, so assume the masses are the same, what you'll see then is that this temperature change depends on C. So if there's a greater C for a given amount of energy, you'll have a smaller change in temperature. Well, that's what's going on with the pizza. The big difference between the crust and the toppings is actually water content. The crust has water in it, but not nearly as much water as the cheese, the tomato sauce, right? All that other stuff. And water has a very high specific heat, right? It's 4,186, right? Which is big. I know that probably doesn't mean anything to you, but other kinds of numbers are not even close to that. Like salt is on the order of 900, 900 compared to 4,000 something. So like just plain old salt is a good 1/4, 1/5 that of water. And so you think about the other stuff that makes up bread or the crust of the pizza, it's going to have similar kind of numbers to salt. And so what that basically means is if the specific heat is 1/5, there's going to be 5 times as great of a temperature change for the crust versus the toppings. So that's another good example of where you've experienced specific heat. So if there's greater specific heat, it requires more energy to warm it up, but it also requires more energy loss to cool it down. So you remember earlier I was talking about how like Seattle and Juneau and all these other places on the ocean stay warmer. Well, the ocean's got a huge amount of heat in it, huge amount of energy, because the specific heat is so high. That's why it will last longer than if you had like all that heat, say, put into rock. It will still keep you warm for a while, right? You heat up a rock, it'll keep you warm, but it's going to cool down faster than an equivalent amount of water. But the same thing goes the other way. Like one of my brothers lives in Colorado, and when he comes out to visit, he always brings me a cooler full of really high quality root beers, like really high quality that you can only get in Colorado. And, so he'll put them in a cooler and bring them. And he's kind of a sciencey, nerdy guy like me, go figure. And so he'll actually like keep track of the temperature. He's got a little gauge in there and like plots it and all that. And he always likes to joke about how well it holds its temperature. And I'm like, well, of course it does. It's, root beer is primarily water, right? It's like 90% water, which means it's going to have a huge heat capacity. And so it's going to require a lot of heat transfer for it to warm up. So anyway, more fun facts where physics is everywhere. And if you don't think that I actually think about this when I'm eating pizza and drinking a root beer, you are dead wrong. I think about it every single time. Okay, so heat will change temperature. It will change temperature of objects. But kind of a quirky thing about heat is that it doesn't always change temperatures. What? You can actually have an object that you pump energy into it, thermal energy. Let's go thermal energy. You pump thermal energy into it, and yet its temperature doesn't change. Well, yeah, that does happen, but it only happens when we go through a phase change, when we go from solid to liquid to gas, one way or the other. And in those situations, the heat that's getting pumped in isn't actually changing the kinetic energy of the molecules, but it's changing how those molecules go together, right? Like if we're going to talk about water, for example, when we freeze water, we've slowed down the temperature, or slowed down the molecules enough so that now they're starting to bond together, right? And so then they start forming a lattice, a structure, and that's what we call ice. Let's say we're going the other direction. We start putting heat into the ice. Well, we're starting to excite the molecules, but really what we have to do is break those bonds. And so there's a certain amount of energy that's needed to break those bonds. Once all those bonds are broken, and now it's water again, we can start heating it up. So here's what it would look like on a graph. Let's graph temperature versus heat versus temperature. All right, so let me switch screens again. So on my horizontal axis, I'm going to put heat. So down here is going to be heat. And my vertical axis, I'm going to make this temperature. And let's say that we're starting with something, actually, you know what, let me go. Let's start with something that is negative temperature on the, yeah, we'll make this Celsius. I'm already in. All right, so let's go temperature Celsius. So let's say we're taking ice, and maybe that ice is cool. So it's some negative C. So as we start putting in heat, we're going to see that the temperature increases. And then eventually, we're going to hit 0. And then we're going to stay at 0 for a while. As that ice starts to melt, we start getting ice and water. But that mixture is staying at 0 Celsius. Okay, now after a while, this starts going up again. Okay, so we're going to keep warming up this water. We're increasing its temperature until it reaches 100. So just so I can have some numbers here, this is 100. And then at this point, we're going to see the same thing, that this is going to flatten out. So we're going to keep pumping in heat, and that water is starting to turn into vapor. So we're going to have this mixture of water and water vapor, but it's going to stay at 100. Eventually, though, all that water will be gone and it'll only be water vapor, and we'll start increasing again. So this is what the graph would actually look like. We'd have some places where we're increasing linearly, and then spots where we flatten out. And it's these flattening out that are where we're changing the state of our matter. Because in here, we're liquid. Down here, we're solid. And then once we get above that, we're gas. And I know I drew this for water, but you would have something similar for anything else as it's going through phase changes. So there is heat that's required to change the state, and those we call latent heats. So we had specific heat was changing temperature, and in this case, we're going to have latent heat. And it gets this name because latent means hidden. So it was called latent heat because scientists saw that there was heat that needed to be applied to make it change state, but it was kind of hidden because you weren't seeing a temperature change. All right, now there are two different latent heats. Like it takes a different amount of energy to take the liquid and turn it into gas as opposed to solid into liquid. And so those two types are the latent heat of fusion, and we use capital L with a little f for latent heat of fusion. And that's the bit when we're going from solid to liquid or vice versa. It's either the amount of heat we need to add to make it go solid to liquid, or the amount of heat we need to remove to make it from liquid to solid. Okay, so fusion, just remember what fusion means. Fusion means to come together. So we're taking this liquid and we're fusing it, we're making it solid. So that's the latent heat of fusion. Now this one up here, this is the latent heat of vaporization. And yes, we use L sub V for that. So we have two types. Again, it's really easy to remember because vapor is gas. So remember, vaporization is when we're switching at the gas boundary. Fusion is when we're switching at the solid boundary. All right, so the question then is how much heat do we actually need? Obviously, it's going to depend upon these quantities, but it turns out it's really easy. The formula is at least the amount of heat that's required to make us leap over one of these boundaries is just equal to mass of the object times how much there is. Or by it, sorry, not how much there is, by its latent heat. All right, so these latent heats are very different depending upon what we're talking about. Water, it's crazy. It's off by an order of magnitude. From solid to liquid, so the latent heat of fusion from ice to water, it's on the order of 3 times 10 to the 5th joules per kilogram. But then if we want to take and go from water to gas, it's on the order of 2 times 10 to the 6th joules per kilogram. So those numbers, they're all pretty well known. They are dependent upon the different materials. But that's how much heat we need to go from one state to another. So it gets really interesting when we take an object that's frozen and say raise it all the way to gas. And we'll look at that. We'll look at how much energy we need in order to do that with some water. But while we're talking about phase changes, let me mention one more thing. You guys heard of sublimation?
I haven't.
No? Okay. So sublimation is kind of a cool thing. And with sublimation, you jump over the liquid phase. You go straight from solid to gas. So remember when I drew that graph, there were like 3 tiers. When you have something that sublimates, they're just the 2. So there's the solid, then there's the heat required to switch you to gas, and then your gas. We call that latent heat, the latent heat of sublimation, obviously. But if you've ever played around with dry ice, which is solid carbon dioxide, it sublimates. It immediately goes from solid to a gas. So if you've ever played around with it or if you've watched video of it, you'll see that it doesn't pool. It just immediately goes into gas. It goes into vapor and goes away. So that happens too. It's just a little bit more rare. Okay, so let's do this. Let's actually look at change in temperature and heat and all that. And let's do this. All right, so I've got my high quality root beer and I want to cool it down. Okay, so suppose our root beer is currently 25 degrees C. And nobody, not even the English, want to drink their root beers at 25 degrees C. All right, so we're going to cool it down. And we're going to cool it down. And we're going to go all the way to 0. So we want it nice and frosty. Okay, so nice icy cold root beer. So what we're going to do is we're going to add ice to it. Okay. So we're going to do this by putting it in ice. That's currently at 0°C. So here's my question, is how much ice do we need? Okay, so this is going to be just so that all of that ice melts to water, but all of the energy that came from that ice melting gets put into the root beer to cool it down. Now, let me help you out with some numbers. Okay, so we definitely need the latent heat of fusion for the ice. And so, like I told you, it's 3.34 times 10 to the 5th joules per kilogram. We also know that the specific heat of water, actually, this will be the specific heat of our root beer. So RB, it's mostly water. So let's just say that it's 4,100 joules per kilogram Kelvin. Right. So since the root beer is primarily water, we're going to use a number that's pretty much the same as the specific heat for water. All right, so the last thing I need to tell you is how much root beer we have. And let's say that our root beer has a mass of, let's go 1/4 kilogram. All right, so let's see if we can figure out how much ice we're going to need. So this is literally a energy balance. All the energy we're going to use to heat up, or sorry, to cool off our root beer. So all that energy is going to come from the root beer and is going to go into the ice to melt it. All right, so let's create the equation with those. Well, if we look at the ice first, or no, let's do the water first. Root beer. So the energy that we're going to need to cool off the root beer, it's equal to M times C times delta T. So we're going to need the 4,100 joules per kilogram Kelvin times the 1/4 kilogram mass times the change in temperature. And we want to drop that temperature 25 Kelvin. So that's the total amount of energy that we have to take away from that root beer. Okay, so if you multiply that out, this ends up being 25,625 joules. So that's what we're going to remove from the root beer. Okay, so then for the ice, we think about what the Q for the ice is, since it's only changing its state, it's going to be whatever its mass is times 3.34 times 10 to the fifth joules per kilogram. So that's just that latent heat of fusion. Well, all that energy is coming from this. So what we're going to find is that that mass needs to be the energy that's being released from the root beer divided by that latent heat. Okay, so if we just go ahead and do that division then, we find that this is 0.07 kilograms. Which is not a lot. We don't actually need a lot of ice to cause this to cool down. Right, 0.07 kilograms, that's going to be like, if we have, well, it could easily fit in my hand. If we had like, I don't know, 4 or 5 like decent sized ice cubes, that would be sufficient to do this. All right, however, we know that this isn't actually quite true. You need a little bit more than this. It's actually 0.767. Because if I were just to put my root beer into a little container that had like 4 or 5 root beers, or 4 or 5 ice cubes, and I just let them melt, there's no way that my root beer gets down to 0. Why not? I don't know, should I back up? I mean, is that fair to say that that's not enough?
Is it because they'll melt before it can even get to that point?
So they will melt faster. And why is that? I'll give you a hint. It's something that we routinely ignore in physics.
I mean, all that comes to mind when you say that is air resistance.
Okay. Yeah, good. By cut resistance, just say
Okay,
air,
yeah, air.
right?
Uh-huh.
If you think about the air and all the other stuff that's just kind of there, then yeah, we have to worry about energy going there as well. So if you think about like the outside is warmer, some of the energy from that outside air is actually going into the ice. So there's less of the energy that can come from our root beer into the ice. Okay, well, that's why like when we're going to go and have a barbecue or something, we bring a cooler. And that cooler is insulated so that it helps limit how much of that energy is going out into the environment. We also tend to use way more ice so that as it melts, there's still plenty to take on the energy from the objects that we want to warm up or the energy that's seeping in from the outside. So in reality, we would need more ice, but just in terms of heating up that root beer, we need 0.0767. All right, now I want to change this a little bit. Instead of the ice starting at 0, let's say that it's colder. So our freezer is actually set at a lower temperature, because usually, like when you go and you get ice from like 7-Eleven or something in that big bag, it's going to be way lower than 0 degrees. See, it's going to be a lower amount. So let's say that it's at, oh, not 5, how about -5? No, let's get crazy. Let's make it really cold. Let's make it -25. And here's what I want to see. Let's find out how much mass we need now. So what we should expect is that the amount of ice is going to change. And what do you think? Is it going to go up or down? No guesses?
Down.
I think that's a good guess. It should go down. We should need less because some of the heat is going to be changing the temperature of the ice before it melts. Okay, well, let's kind of set this thing up and see what's going to happen. So I am going to have to give you one more number that I haven't given you before, and that's the specific heat of ice. But I've got that number for you. It's around 2100 joules per Kelvin, kilogram Kelvin. So let's break it down this way, though. We're going to have two things happen with the ice. There's going to be the change in the temperature, and there's going to be the latent heat change. Okay, so this first bit is going to be changing the temperature, and the second piece is going to be, again, the melting of the ice. And again, for the root beer, all it's going to have is the M times C times delta T. It's going to have its temperature change. All right, well, for the ice, let's factor out the M, because that's what we're trying to solve for, right? So that's going to be C times delta T plus the latent heat of fusion. So if I put this all together, I'm going to get the mass of the ice that we need. It's going to be the mass of the water times its latent heat, or sorry, its specific heat, which I think we said was 4100, times its change in temperature, which was 25 degrees. We're going to divide that by the specific heat of water times its change in temperature, and the specific heat of water, or sorry, of ice is 2100 times its temperature change, which is also 25 degrees. And then we need to add to that the latent heat of fusion, which again was that 3.34 times 10 to the fifth. All right, so let me grab my calculator and we'll run these numbers. And my calculator spits out 0.066. I'll put one more on there. 0.0633 kilograms. All right, so check it out. If we started with ice that was at -23, we need 66.3 grams. When we started with it just at 0, that was what, 76.7? So it got reduced by 10 grams. That's not much. That's like half an ice cube. So kind of crazy that it didn't really change the mass that much. It did go down, but only by 10 grams. Well, that's because way more energy is needed to change its state than to change the temperature. I mean, just look at what we're dividing by. This extra bit for the warming of the ice, it's on the order of, what's that, 5 times 10 to the fourth? So it's on the order of 10 to the fourth, which is 10 times less than the latent heat. So it turns out that the vast majority of heat is used to change the state of objects than to change their temperatures. A lot of energy is required to either break or build bonds. Anyway. Okay, so there's something else that happens with heat as we get changes in state. All right, well, I'm going to stop for today, so I'm going to pause.